this video we're going to look at Biot-Savart's law, Amperes law, solenoids and hopefully forces between two parallel wires. So the first law here to do with magnetic fields is Biot-Savart's law. Basically what we already know at this point is that a current can create a magnetic field going around it, as we discussed in the previous videos, like a circular field. The field itself, of course, will depend on the current. It depends on how far away you are from the wire and the shape of the wire as well. It could be curled, it could be in a straight line. That will all affect the magnetic field around it. It will make a slightly different effect. So if you have a wire, an external field around it, you know that the wire is a straight line, will have a circular field by itself. You know, if you have a curvy wire, you will have a field, but it will be at different points, the field will be different. So there are different situations that we need to be able to deal with. The first one is a curvy, bendy wire, something like this, like a wire that's moving around. And of course, if you take the field from different parts of the wire, you will have all these different small angles. So in order to figure out how to find the field, this is the dB, this is the magnitude of the field, we will use the permeability of free space divided by 4 pi, multiply that by the current, multiply by how long the wire is, multiply that by how far away from the wire you are, so this will be my radius, this will be my ds, sometimes known as L, as in length, and the angle. We will choose one point and we will choose an angle that's related to it. Okay, so that's how you will do it for a point P. Sometimes it's shown like this, same idea, but sometimes you won't have the sign of the angle, it will give you R hat. This is exactly the same thing, it's just the angle between the two, so radial direction only. Okay, and moving over to Amperes law. We know that the sum of the magnetic field on each small length is mu multiplied by the current. This is what Ampere states. He says if it's a circular, we can write it as P 2 pi r. What does he mean? Essentially, he figured out that the current affects the field. A bigger current means you will have a bigger field. So he decided to do some experiments, and he found that if he sets B equals to mu I, he can find out the rough idea of what the field will be. In short, you will see the formula looking like this. BL equals mu I. This is the general way it will be written. A magnetic field times by the length of the area that's enclosing, equals to mu I. It's sometimes written as ds as well. Remember I mentioned the previous one, we had ds. It can sometimes be written as that. An example that you'll get in a simple introduction is to rank each of these enclosed dotted lines from the highest magnetic field to the lowest magnetic field. Charged my laptop, sorry. So then, if we were to do that, what we do is we'll draw a circle around any of them. There's A, B, C, D. I can start with D. Here is D right now. If I enclose D, for example, here is the dotted line for D. I can see 5 is coming out, 2 is coming in. No problem. I can just do 5 minus 2 because they're going in opposite directions. So in total, we have at D, we will have 3 amps. And essentially, you can say 3 amps going out if you wanted to. You will do the same thing with all of the other ones. And I actually already did this with you. So let's go through the answers. Here we go. It's already been done. We've got 5 minus 2, we've said 3. If I looked at C, which was in blue, we've got 5 and 1, same direction. 1 plus 5, 6. If I looked at B over here, we have 2 and 1. 2 is coming out, 2 is going in, 1 is coming out. This is this one over here. That means, of course, 1 minus 2, you can say minus 1, or you can just say 1 going in. It's just the magnitude we need. Finally, if you take the whole enclosed loop, you take all 3 of them, 5 and 1, but minus 2. 1 and 5 minus 2, of course, is 4. Ranking them in order from the highest magnetic field, we know that the highest current will have the highest magnetic field, which means C will be the highest, followed by A, followed by D, and then B. So now we can take that same formula and we can rearrange it around a little. We can change the current, we can change the distance from the wire. We know that the magnetic field is circular, so this here will be circumference. So we can take that BL and we can rearrange. So BL, L being the circumference, we can change that to 2 pi r. I'll take the 2 pi r to the other side, and now we have a formula to find the magnetic field in a long straight wire. This is just for a straight wire with a current flowing through it. You've got a curvy wire, now this one is a simple straight wire. B equals mu I over 2 pi r. And this is how it would look. Same permeability of free space, everything else stays the same, distance from the wire is the radius, and so forth. So this is the wire, and the radius is how far away from the wire you are. So as you realize, actually there's one thing I didn't mention. If you are inside the wire and you're getting bigger, you're catching more electrons in this little radius, which means more current, which means the actual field will get bigger and bigger because we're catching more of these electrons. So the field inside the wire is big, but when you go further out, it will be reduced because there are no more electrons around here. This is just empty space. So you will find that the graph, if you were to see a graph, from inside the wire going all the way to here, this is when you leave the wire. So I can say inside, and this is outside. That's a D, by the way. Okay, so we did some practice problems in the class. You have the field strength of 2 centimeters, you have the current of 2 amps, you can find the magnetic field. Mu I over 2 pi r, put your numbers in, centi must be in meters, and you'll get your answer. If you double the current, you will double the field. If you double the distance, the further away you are, you will half the field. It gets weaker by half. Okay, and again, another problem that we covered here was that we have a coaxial cable, current going one way, current coming out. If you enclose a small area, which is just this one, we do not care about the current outside of the area, only what's enclosed, I1 in this case. Part A asks you to find the field in cylinder 1, so we will use mu I over 2 pi r as normal. This has 3 amps going through it. So all we did was that we did 4 pi times 10 to the minus 7 times by 3 over 2 pi times by this radius, which it told us already, right there. That's in centimeters, must make it meters. Part B was the bigger area, all of this, which means we have a current going up and a current going down, just like we did at the start of Amperes' law. All we do is we take the 2 currents, 3 opposite directions, so 3 minus 1. This is 1 amp going in the opposite direction. It tells me that it's 1 amp going in the opposite direction. And we got that solved. And these are 4 scenarios that we actually don't need to worry about too much. I doubt that this will come in your exam, but inside, if you want to know, there are 4 scenarios. Inside the inner conductor, between the inner and outer the conductor, inside the outer conductor, and outside the outer conductor. So you have inside the small wire, outside the small wire, inside the big wire, outside the big wire. That is the 4 different scenarios. So if you look at this, you can see the field lines, they're going in circles around the sides, but in the middle it starts to straighten out. This is if I use a loop of wire or a coil of wire like a solenoid. So this is what the 3 key points. Circle, curved, straight in the middle, uniform in the middle. And that is where solenoids come in. If you keep wrapping it around, you will have a nice long straight magnetic field passing through. And it looks just like an actual magnet. The solenoid looks like a magnet. In the center is the strongest. Outside the field gets pretty weak. So we don't need to worry about the fields outside, we only care about what's inside. If I take my solenoid and I cut it in half, this is like the wires going around like this. This was like the wires going around. If I take this and I cut it in half and I'm looking at it from the front, we can figure out how to find the magnetic field inside this solenoid. We need to know it's the sum of all the fields. We would have this perpendicular one, this one over here, A to B over here, D to C, so we'll have them all. We've already agreed that these 2 will be perpendicular, so they will not count. We know that D is not going to happen because it's usually too weak for it to be worrying about. So we only really care about this length from A to B. Doing that, we can just see how many turns we have in this, so we can see how many wires there are passing through. So we'll have our BL, and we'll have a mu, the number of turns, and of course the current that is passing through. So that takes us to a nice little formula, bunny over L, or bunny, known for short. If you have N, which is N over L, the number of turns per the length. If this was, I don't know, 2 meters, and I counted I had 1, 2, 3, 4, 5, 6 turns, for example, you'll do 6 divided by 2. That's 3 turns per meter. And the formula can look like this. Bunny over L. Number of turns, the current, the length of the solenoid. And again, you can do the N over L, you can replace it with just the number of turns per length. Okay, so more turns, more current, increasing the length, you need to know what will happen. So this is how you'd find the magnetic field in the center of a solenoid. Increasing the number of turns, of course, will make it stronger. If you increase the current to make it stronger, if you make it a longer solenoid, it'll get a little bit weaker. And the material that travels through, of course, is free space. So we use the permeability of free space. Now, if you have 2 wires with current flowing in opposite directions, you will see that if you have, using your right hand rule, the magnetic field will be coming out and around. This magnetic field is going to be coming out and around. In the middle, they happen to be pointing in the same direction. So if you were standing in between 2 wires, you will have 2 fields here pointing inwards, which means if you wanted to find the total, you will add the 2 fields, mu I over 2 pi r plus mu I over 2 pi r. So you have to know if they're going in the same direction or opposite direction. In this case, opposite, add. If they were going in the same direction, you will subtract, because one field will be going into the page, one will be going out of the page. Like in this example here. Looking at this one here, the top wire, and this is going to the right, current is coming, and the field, is coming out and then in. Same thing, is coming out and then in. In the middle, one of them is going in, one of them is coming out. So the fields will have to be subtracted. So don't think you will add the currents. You will, to get the field, you will have to subtract the 2. Okay, mu I over 2 pi r minus mu I over 2 pi r. Get your answer, and whichever one is stronger will win. Okay, so the force between 2 current carrying wires, a little bit different now. You can calculate the force using the formula that we already know, LIB, lib sine theta. It's perpendicular, so sine of 90 is 1. I can ignore that. What I can do is, if I want to find the force on one of the wires, I need to know the length, the current, and the field that he is in, the external field. He will be in a field due to the other wire. So I can calculate this wire's field with the same formula, mu I over 2 pi r. R has been replaced with d because the radial distance is just simply the distance between the 2 wires. So you can write R, you can write D. Putting that in, you can get a nice new formula. Rearranging it, shuffling it around a little, you'll get fuel over 2 pi d. Mu I1, I2 times by the length, of course the length will be the same, over 2 pi d, same distance between them. And the forces are equal and opposite. Newton's third law. You calculate one, you will know the other. Simple as that. Okay? You don't really need to worry about how or why the forces are going to be like this, but I can show you. If you wanted to find the direction of a force on one of the wires, for example, let's say we have this wire, and he is in the magnetic field due to him. He is on the left of this guy over here. Okay, so this magnetic field, if you use your right hand rule, the grip rule, in fact, the magnetic field is coming out on the left. He has a field coming out. He is inside a field coming out of the page. He has a current going up. By doing this, if the current is going up and the field is coming out of the page, using your right hand rule again, this is the 3 fingers, the force will be pointing to the right. He will become attracted to him. Likewise, he is in his field, and on the right hand side of him, the field, the blue ones here, are pointing into the page. Using the same rule, he will be attracted. So, long story short, if the current is going in the same direction, they will be attracted. The forces will be attracted. If the currents are going in the opposite direction, they will be repelled. That's the main thing that you need to know. Same direction, attraction. Opposite direction, repel. Okay? Easy. So that's what I've written over here. Okay? We did some practice questions using fuel. U, I, 1, I, 2, L over 2 pi r. We need to find the magnitude and direction. We know that they are going in opposite directions, so they will repel. You solve for the numbers, and you will get 1.1 times 10 to the minus 2. And I gave you one final thing about the field around a loop. This is if you have a loop and you're horizontally away from the loop. Like this is the x-axis over here. You can calculate the magnetic field along this x-axis. You just do mu I over 2r. The radius, which is the radius of the loop itself, squared over, bringing in a bit of Pythagoras here, x-axis squared, the horizontal distance, plus r again itself, to the power of 3 over 2. That will help you find the magnetic field along the x-axis, horizontally away from a loop. Very nice.